Hi everyone. It's a little early, but I'm gonna try to get a picture of my dog up because I've had a request. So see if I can do that. Uh, there we go. That's my dog. His name is Daniel. No problem. What took me a long time was just finding a picture. I have them all over the place, and I just didn't have one ready on my desktop. Yeah, he's a 12-year-old. Um, Total mix. I did the DNA test, and it turns out he's a quarter. Um, let's see, what was it? A quarter boxer, 1/8 yellow lab, and oh, what happened here? 1 second, guys. I just need to. I think I accidentally closed the wrong window. Sorry about that. I think I might have accidentally just closed the window. But can I have confirmation that people can hear me right now? Oh, okay. Yeah. Thank you. Thank you. I accidentally closed the chat window. All right. Yeah. What was I saying? He's a quarter boxer, 1/8 yellow lab, 1/8 golden retriever, 1/8 German Shepherd, 1/8 Doberman Pinscher, and the other 1/4 was unknown. So he's like about as mixed dog as you can get. All right. Let's start. Uh, Let me switch back to wherever. There we go. Okay. Oh, oh, great. I made the window so huge now. Go fix this. Let me see here. Squeeze that down. There we go. Yeah, and the software I'm using is actually known as OBS, and allows me to move windows around, and um, it's kind of fun. It's used for a lot. It's used by a lot of YouTube people that do streaming. First of all, I wanted to apologize. I remember last week I was only supposed to lecture for 1 hour, and the last live stream, I mean, I actually went for an hour and 15, so I went longer than I should have, and I apologize. But this today's live stream should be fairly short. I'm just going to go over what's on the test, and we'll do a few questions. We won't do all possibilities because I won't do the 2D kinematic stuff because we just finished doing that. And if you have any questions, I'll answer them. The usual question that everyone asks is, how many how many questions are on the test? And I finished it today. It's 24 questions. Okay, and you should have one. You should be able to do it in an hour, but I'll give you, like I said, 2 hours to do it, just in case you have any technical difficulties or anything like that. And before I jump in, maybe I should also tell you like how you should study for this. I mean, obviously, it's going to go over the pre-recorded, the materials, the pre-recorded videos that I've given you. That's the material. The live streams were just a repeat of that. They were just practicing that. And so what you should do is probably go through the PDF notes, or rewatch the videos if you have the time. And when you see that I do those examples, the example problems, try to repeat those example problems on your own. Like I start off with the word problem, and so you could just write down that word problem, and then don't look at my solution. See if you can repeat it. And if you can't, then take a look at how I did it. Otherwise, if you can repeat it, try it again. Just change some of the numbers around. And, it's not that big of a change, just changing numbers, but try to do it with some different numbers, see what you get. And, and do that with all the problems that we've done, and you should be good. Also, the assignments that we've done, you can repeat those problems. You can repeat variations on them. And during the live streams, I gave you a few extra problems here and there. Try to do those as well, okay? And the test will have basically those kinds of questions on it. All right, so what are the topics that are on it? Let's start off here. The first topic, and I won't even do an example of this because these are fairly straightforward, was measurement and unit conversion. Okay, and the thing you really need to know here, I mean, most people have done unit conversion before, but what you need to know is that we use MKS in this course, and it's not just the metric system, it's the metric system with a particular choice for the base unit for length, time, and mass. And those are for length we use the meter, symbol M. For time we use seconds, and for mass we use kilograms. Okay, not grams. That's a typical mistake that's made. Some people will think, oh, it's you should be using the base unit like grams. No, it's actually kilograms. We haven't had a chance to use mass to measure mass yet, but we will. Right after the test, when we start with Newton's laws, we'll talk about what mass is. Okay, so that's for that one. And now let's continue with 1D kinematics. And I'll do a quick little problem. So we did general 1D kinematics. You're the non-calc course, so really there's not much that you can do in general kinematics without calculus. Okay, so general kinematics, it means that there's no restrictions on like the motion at all. It could be any function that describes the position as a function of time. The only thing you really need to understand out of that is how the average velocity is obtained, like that. Okay. And there's also the average acceleration, but I won't ask a question directly about average accelerations. They're a little bit harder to understand, and they're not as meaningful as average velocity. But what an average velocity is, in contradistinction to an instantaneous velocity, is that an average velocity is measured over some interval of time. It doesn't mean that you're traveling the same speed during that interval of time. You could speed up, you could slow down, but on average, you've traveled so far in so much time. And so you have a delta x, which says, how far did you travel over the time, and divide that by delta t, and that's what gives you the velocity. Okay, and it's called average because it's over an interval. Instantaneous, it's technically the same formula, which may seem strange to a non-calculus students, but the delta t is made extremely short. Okay, and so that's how it transitions from average to instantaneous. Okay, so here I just give you a very quick example of the kind of question I could ask. I simply tell you, what's the average velocity between t equals 1 and t equals 2 seconds? And you know what, I didn't word this well. Maybe I should just say given that the object is at x equals 5 meters at 1 second, and x equals 21 meters at t equals 2 seconds, like that. Okay, so let me just maybe fix the wrap a little bit here. There we go. Okay, so where's the average velocity between t equals 1 to t equals 2 seconds? And put the seconds in there. Okay, like that. Given that the object is at 5 meters at 1 second and at 21 meters at 2 seconds. Okay, so if you've got you want to write this in functional notation, the position at t equals 1 is 5, and the position here at t equals 2 is 21, like that. Okay, and here's the formula. The average v is delta x over delta t. So what's delta x? So that's like where you are at 2 seconds minus where you are at 1 second, and that's 21 to minus 5, which is 16 meters. Okay, and the delta t is you end up at 2 seconds. You started at 1 second, so it's 2 minus 1 second. It's always the final minus the initial, which is 1 second. And so delta x over delta t is 16, and the units are meters per second, like that. Okay, so that's really it. It just tests to see if you understand intuitively what velocity is and how to calculate it from position. Um, and the average is it's exactly that. It's an average. It doesn't tell you how fast you're going. So if you were on a trip, and you could say on this trip I was traveling 60 miles per hour on average during the whole trip. That doesn't tell you how fast you were driving, I'd say 1 minute into the trip or 2 minutes into the trip, because you could be driving faster sometimes and then slower and then faster and then slower. But on average, it would work out to say 60 miles per hour or something like that. Okay, so there's that's the only thing that really I could ask a non-calc class about um, general kinematics. Okay, the constant acceleration, we can do a lot more. Okay, and constant acceleration, the formulas are these three formulas here. Okay, and so maybe I should describe the variables that are in them. There's x and x naught. That's x naught is the initial position, final position x, and the initial velocity is v naught, and the final velocity is v, and a is the acceleration, and t is the time over which the motion occurs. 1D means it's along a straight line. Okay, and constant acceleration means that it's speeding up or slowing down, but always at the same rate. So this applies to problems like falling. Okay, if I drop a rock from some height, as it falls, it accelerates downwards at 9.8 meters per second squared. We're going to round off to 10 meters per second squared on the test, as we've done throughout the course, just for simplicity. Okay, but it doesn't just apply to falling. It could also be if you're driving your car and you step on it and you accelerate, you speed up, or you step on the brakes and you slow down. Okay, if you do that at a constant speed, you can you also have that these formulas will apply. Okay, and so let's do a quick example of that. All right, so this is again constant acceleration 1D. So here I have a car, and it's driving at 65 kilometers per hour, and it speeds up to 100 kilometers per hour over a distance of 100 meters. By the way, I mean, if you drive on the other side of the border, you have a feeling for how fast a kilometer per hour is. 65 kilometers per hour, that's like 45 miles an hour, and then or 40, something like 40, and then 100 kilometers per hour, that's like 55 miles per hour. Okay, so this is a typical thing you might do on a highway as you speed up, and 100 meters is about 300 feet. Okay, and then I ask two questions. I ask, what is the acceleration, and how long does it take to speed up? Okay, so this one's almost, these problems, I mean, now that you've done 2D, and 2D is so much more complicated than 1D, you could almost do these like, picturing the picture in your head. But it's probably better that we actually draw the picture, okay, not make a mistake. And even on the test, just in case you get confused, because it's very easy to confuse initial and final values here, and then you get the wrong sign, something like that. So let me switch to the whiteboard, and I'll draw it for you. Okay, and so the first step is just draw a picture of what you're going to see. All right, just draw a picture of what you're going to see without any coordinate system or anything like that. Whoops, that's all right. There we go. Okay, we see how this is coming out there. Okay, this looks good. All right, so so there's the car initially, right here, and this is when you're traveling at 65 kilometers per hour, and then you speed up to 100 kilometers per hour. And I mean, really, you're trying to draw a movie, but of course you can't draw a movie. But all during this period in between here, you're speeding up. So the second step then is to add a coordinate system, and that just means put a ruler and also a stopwatch. Okay, so the ruler is the x-axis. All right, there we go. And we'll take positive x to the right, like that. And you know, when you go to measure something with a ruler, you get to choose wherever you put the zero. And so let's say as soon as you start to accelerate, that's going to be your zero. And that's going to occur right here. Okay. And we'll measure from the back of the car right there. Okay. And that's our initial. So that's t equals 0. When we say initial, we mean t equals 0. And so that's your initial position. And that's the 0 on the ruler, like that. Okay. And then sometime later, and I don't know how much later because I didn't tell you. If you reread the problem, we'll look at the English again in a second, but if you reread the problem, I don't tell you how long it takes to speed up, but it speeds up and over some time, and it takes 100 meters. I tell you that it takes 100 meters to speed up to 100 kilometers per hour. Okay. And over here, there's also the initial velocity. And if you read the problem, the initial velocity was 65 kilometers per hour. All right. And the final velocity was 100 kilometers per hour, like that. All right. And that's the last step. Okay, after you draw the coordinate system, then start measuring your values off of it. And you should go in this order, or have some order that you've memorized. I do initial position, then final position, initial velocity, final velocity, and time, and acceleration. And we actually don't know the acceleration. Okay, and so those are the quantities that go into that equation, and you could quickly read them off the image here, the diagram. Okay, so again, initial position, initial velocity, final velocity, acceleration, and time. All right, let me switch back here. Once you've got that, you should write those values down, and here they are. I've written them down right there. Okay. And then I guess the next step is make sure that everything is MKS. Okay, so I tend to do my problems in MKS, but not always. Okay, so in some questions, I give you the numbers in non-MKS, still metric system, but non-MKS units you have to convert. And in a few, I expect you to convert the answers to non-MKS units. Okay, so for instance, in some question, I forget which one, I expect you to be able to go from meters to kilometers. Okay, which is the opposite of what you do here. So the velocities are not in meters per second. We have to convert them, and so here's the initial velocity. Okay, it was 65 kilometers per hour, and unit conversion, I showed you this general way of doing it, but there's certain units that we convert so often. Kilometers per hour to meters per second is very typical. It's just divide by 3.6. Okay, and you go, well, why does it work out like that? Well, because to convert it, from kilometers per hour to meters per second, it's like multiplying by 1,000 to convert kilometers to meters, and dividing by 3,600 to convert hours to seconds, because there's 3,600 seconds in an hour. And so if you multiply by 1,000, but you divide by 3,600, that's like dividing by 3.6. So 65 kilometers per hour, that's 18.1 meters per second. And 100 kilometers per hour, that turns out to be 27.8 meters per second. Okay, and so we've got now all of our kinematic quantities here in MKS units. And at this point, you just choose the equation that you want to use, or that you have to use in this case. You don't have time, and if you take a look at these equations, the first and the second equation require time. Okay, and so you can't use them because you're trying to find the acceleration. That's the first question. What is the acceleration? Okay, and you don't have the time, so you're trying to find A. And equations 1 and 2, they have A in it, but they also, A is unknown, and so is T. So that's not going to work. It's only the third one that's going to work. So chances are, if you have a question which doesn't have time in it, go to equation number 3, and that should do it for you. All right, so here it is. Okay, v squared is equal to v naught squared plus 2ax minus x naught. All right, and then substitute in the values. For v here, we have 27.8. For v naught, we have 18.1. 2 times a, that's what we're solving for. X minus x naught, that's how far you traveled. Okay, so we started at x naught of 0, and we went to 100, so 100 minus 0 is 100 there, like that. And then the next line is I just simplified that. Okay, so 27.8 squared is 771.6, and 18.1 squared, 327.61. And then plus 2 times 100, that's 200a. And then solving for a, I get 2.22 meters per second squared. Oops, meters per second squared. There we go. And that gives us the acceleration. Let me see if there's any questions in the chat here. All right. Okay. So I don't see any questions. And you should always ask yourself at the end of these, do the numbers make sense? When I put together these problems, I mean, I'm making up the numbers, but I'm trying to make up numbers that are reasonable. Like, driving 40 miles an hour and speeding up to 55 miles an hour, or 65 kilometers to 100 kilometers an hour. That's pretty reasonable. That's something that, most people have done in their lifetime, right? Something like that. And when that happens, I mean, when you speed up, you feel that you're being pulled a little bit back into your chair, a little bit, not a lot, but and you take a look here and you go, oh, I got this number 2.22 meters per second squared. Think about a number, an acceleration that you can compare that to. And there's one acceleration that everyone experiences, and that's the acceleration due to gravity. That's 9.8 meters per second squared, and that's about 2.22. It's like a little more than a fifth, okay, like a quarter of the acceleration due to gravity. And that makes sense, right? I mean, if you've gotten twice the acceleration due to gravity, that would be way off, because when you're driving, you don't feel like you're being pulled back into your chair with twice your weight. That would be crazy. That happens maybe in a jet, but not in a car. So yeah, that seems about reasonable. Okay, and then the other question I asked was, what is the acceleration and how long does it take to speed up? At this point, you're looking for time, and you can use either equation 1 or 2. Let me just show you those equations again. You can use either equation 1 or 2 because they both have time in it. But you don't want to use 1. Well, you can use 1, but it's more complicated, so obviously use number 2 to solve for the time, because now we have the acceleration, and you can solve for the time there like that. Okay, so v, the final velocity, was 27.8. A was 2.22. T is the unknown, and v naught 18.1. Solving it, you get 4.37 seconds. Okay, and that again makes sense. It takes some time to speed up. It's not going to take you like 3 or 4 minutes to speed up from 65 to 100 kilometers per hour. Okay, you're not going to speed up in a fraction of a second. 4 seconds is about right. Okay, I mean, just don't go speeding on the highway, but when you go on an off ramp on the highway, just think, how long did it take me to speed up? 4 seconds sounds about right. Okay, again, just to do that, just so that the numbers seem reasonable, I'll be honest, I mean, some of my numbers, the incorrect answers are way off, and so that should help you, because it's you're going to calculate this, but you can immediately eliminate a few of the answers, because they're just going to be crazy numbers, and so that helps you to narrow down the correct answer. All right, let me see if you've got any questions with 1D. I mean, at this point, it should be fairly straightforward. On 1D, constant acceleration should be fairly straightforward, especially if you've been practicing the 2D. Okay, because everything in 1D is kind of subsumed into the 2D stuff. All right, another 1D problem that we did was a harmonic oscillator. Okay, and so there are lots of things which just vibrate back and forth. Okay, like everything, like in biology, this is how you can hear me right now. These little cilia, these little hair-like structures in your inner ear, and they vibrate back and forth. They all have different sizes, so they all vibrate at different frequencies. They vibrate back and forth. So there's an example of vibration, but it could be anything from something that small to like a pendulum vibrating back and forth, a swing at a playground vibrating back and forth. There are lots of things which vibrate back and forth. And so this is quite generic. Harmonic oscillator is quite a generic type of motion. So we studied in the abstract. Okay. And there are the equations you need for that. Okay. So there's this quantity omega, which is called the angular frequency. It's not something you measure in the lab, but it comes up a lot, not only with the harmonic oscillator, but later in the course too, and even next semester. So this is a good time to introduce it. And this angular frequency is related to the period, which is something you can measure in the lab, and the period directly. And the period is just how long does it take for an oscillator to make one complete cycle back and forth. Okay, so if you're starting at this end here and you go one way and then back again, the time it takes to make that one complete cycle, that's known as the period. It's given the symbol capital T. So the angular frequency is 2 pi over capital T. So as soon as you get the period, you've got the angular frequency. Or conversely, if you have the angular frequency, you can immediately calculate the period. They're like the same quantity, but just cast in a different way. Okay, and there are 3 different maximas that occur during this motion. The first one is the amplitude, A. And so, as the thing oscillates back and forth, it's symmetrical around the middle here, like that. And so you could just say, oh, how far did this thing oscillate to the one side? Okay, and that's the amplitude. And if it oscillates a certain distance to the one side, it'll oscillate the same distance on the other side, maximum distance on the other side. That's the amplitude, okay? So amplitude, maximum displacement. Vmax is the maximum velocity. That occurs when the oscillator passes through equilibrium. So at the end points, the velocity is 0 because it has to stop, turn around, and go back. As soon as it stops at an end point, the velocity is 0 and it comes back. Okay, so the velocity is 0 at the end point, 0 at the end point. It's maximum as it passes through the middle. Okay, that's where Vmax occurs. And so I say here Vmax equals omega A. That's the formula, but you also need to know where it occurs. It occurs at equilibrium. Okay, and then Amax is the maximum acceleration, and it occurs at the endpoints. And actually, I should have also written maybe that the acceleration is 0 at the middle, but it's maximum at the endpoints. Even though the velocity is 0 at the endpoints, the acceleration is maximum because that's when the oscillator is being swung around the fastest at the endpoints. And it's given by maximum acceleration equals omega squared A. Okay, so not a lot of formulas there, but there they are. Okay, and let's do this problem here. Whoops, you can't read it all. Now you can. All right, so an oscillator is found to have a period of motion of 2.5 seconds. Okay, and I could have said that a different way. I mean, there I say it's the period, but I could have said it makes one cycle in 2.5 seconds, synonymous. Okay, so and the velocity is found to be 10 meters per second when it passes through equilibrium. Okay, and the first question is, what is the maximum velocity? And it's almost a non-question because you go, well, you just told us that it's 10 meters per second, but it's kind of subtle because I didn't say that the maximum velocity was 10 meters per second. I said it's that the velocity is 10 meters per second when it passes through equilibrium, and I expect you to know that velocity at equilibrium is the maximum velocity. Okay, so I'll make sure that you understand, which points in the cycle you're getting the maximum velocity and the maximum acceleration by asking it in this sort of way. Okay, so if I ask for the acceleration at the endpoints, that's equivalent to asking for the maximum acceleration. All right, I hope that's clear. It's not meant to be tricky. It's just meant to make sure that you understand which points in the cycle you're getting the maximum. Okay, so that's one. Now the next one is what is the amplitude? Okay, so I don't give you the amplitude in the English here, but I do give you the maximum velocity. So you know now that Vmax is 10 meters per second, and you don't know omega directly, but I give you the period. And again, as soon as you have the period, as soon as you have t, you've got omega. So there, what you want to do is you want to calculate omega first, and once you have Vmax and you have omega, then you can calculate A. Okay, so I say here first, use that omega is equal to 2 pi over capital T, and just plugged it in, and I found that omega turns out to be 3.77 hertz. Okay, so 2 times pi, it's 2 times 3.14 divided by 2.5 works out to 3.77. The units are hertz. It's actually exactly the same as 1 over seconds. Okay, so you should know hertz. It's going to show up all through the course, But it's probably better to think about it, or at least when you're working with units, to write at 1/2, because that shows the time unit very clearly. But hertz is what you would see on instruments and things like that, so you need to know them both ways. Okay, as the course goes on, you're going to see that we're going to get more and more complicated units. They're always going to be in terms of length, time, and mass, but because they get more complicated, we kind of glob them all together and give it a name. So for instance, after the test, I'm going to introduce a Newton, which is just a kilogram meter per second squared. Okay, but rather than writing kilogram meter per second squared, we just write Newton. Okay, and same thing here. Rather than writing 1/2, we just write hertz. All right, and so now that you have omega, we know that Vmax is equal to omega times A. Well, we want to solve for A, so isolate A by dividing both sides by omega. A is equal to Vmax divided by omega. That's 10 divided by 3.77, and you get 2.65 meters. Okay, so there's your amplitude for this oscillator. Okay, and then the last question is, what's the maximum acceleration? There's the formula. There it is there. We know all the pieces. There's no rearranging that you have to do here. You just got omega squared times A, and that gives you 37.7 meters per second squared. By the way, that's a pretty big acceleration, and oscillators can have large accelerations, okay? So that's not an unusual number. I mean, you don't have any intuitive feeling for that because, like, unlike the car example where you've actually experienced cars accelerating, you haven't been on a lot of oscillators. Maybe a swing at a playground, okay, something like that. All right, let me see if there's any questions with that. All right. Oh, wait, there is one. I got 2.51 hertz. Is there something? 2.51 hertz? Oh, did I do something wrong? Let me just bring up my calculator and try again. Geez, I hope I didn't make a mistake there. So, oh, maybe I did. 2 times pi divided by 2.5 is equal to. Oh, geez. I have no idea what I did there. Wow. Egg on my face. Okay. Yeah, Josh, you're absolutely right. Okay. So thank you for pointing that out. Yeah, it actually turns out to be 2.5. I don't know what I did. I must have just, like, when I did this earlier today, when I typed it on my calculator, I must have just done it wrong. Well, okay, then you know what? Our answers change. So I better fix that for the class. Okay. And so that's going to be roughly 4, but I might as well get the exact number here. 10 divided by so I get this number here. All right, and let me round it off. Okay, and then for the maximum acceleration, of course, that's also going to change because now this is going to be different, 2.51, and the amplitude is going to change as well. That's 3.99, it's close to 4, and 2.51 squared multiplied by 3.99, and I get that acceleration there. Okay, and again, let me just round that off. All right, so let me just quickly repeat that. It looks like the angular frequency is 2.51. The maximum velocity turns out to be, the amplitude turns out to be 3.99 meters per second, and the maximum acceleration is 25.1 meters per second squared. Is that what you guys got? If that's the case, then I'll move on. I have no idea what happened there. I must have been going too fast when I did it earlier and got the wrong number. But yeah, Josh, you're absolutely right. It's the angular frequency was 2.51, and then of course the error propagated through. By the way, if that happens on the test, chances are you'll know right away because your number won't match any of my numbers. Okay, and so you'll know that there's something wrong. Okay, with the multiple choice. All right. Okay. If there's no other questions with that, let me see here. All right, looks like you guys are okay. Let me go on to the next thing we studied, which were vectors. Okay, and vectors. We need those because we're going to do 2D kinematics, and all the kinematic quantities in 2D, like initial position, initial velocity, final velocity, acceleration, they're actually vectors now. They have to be pairs of number in 2D. Time remains a scalar, remains a single number, but the other things are vectors. And there's lots of ways of representing vectors in 2D. They're always a pair of numbers, but how you interpret the two numbers is different. Okay. And we're only going to study two, which is polar and Cartesian. And the polar, I give you r, which is the magnitude of the vector. That is how long it is, or how, if it's a velocity, how fast it's going, irrespective of the direction. And the other one is the angle or the direction. Okay, so either I give you r and theta, and I expect you to calculate x and y. Okay, or the other way around, I give you x and y. All right, I give you x and y here like that. And I expect you to calculate r and theta, okay? And so you're converting from one to the other, all right? Now, I don't want to do one of those problems because they're pretty straightforward. I think almost everyone got perfect on the assignment on vectors, okay, where I had just conversion. I probably should have asked you one other question in that assignment, and I did mention it, and then I kind of forgot to ask it as an assignment, but it is going to be on the test, and that is how to add vectors. And for now, we'll just add vectors in Cartesian. So let's take a look at how you do that, okay? So when you have two vectors that are in Cartesian, I give you the Cartesian coordinates for the two vectors and ask you to add them together. How do you do that? Now, we don't really need that for the kinematics, but we're going to need it as soon as we get back after the test and start up after the test. And that is because we're going to have forces, and the forces are going to add. And so we have to know how to add vectors, at least in the Cartesian representation. Okay. And so in this question, I say I have one vector, which is x. I called its x component x1 and its y component y1. So I have x1, which is 5, and y1, which is 5. So the x and y component of the first vector is 5 and 7. And the x and y for the second vector is -3 and -5. And I want to add those together. And the way it works is to get the resultant x component, you add the x components of the two vectors. Okay, so to get the resultant x component here, you just add x1 and x2. All right, so you take the x component from the first vector, 5. You take the x component from the second vector, -3. You add them together and you get 2. Okay, and to get the y component, the resultant y component, you take the y component from the first vector, you take the y component of the second vector, you add them together, so it's going to be 7 minus 5, and that's also 2, like that, and that's your resultant vector. Okay, so I probably should have asked one of those questions, but it's fairly straightforward. But of course, if you don't know to do that, then you might get confused on a test. Okay, so that's how you add vectors. All right, let me see if there's any questions in the chat here. I don't see anyone asking any questions here. If you want, if you want to see a conversion problem, like I said, most people did those right. We can do one after I get through the other topic here, but that's basically it for vectors. Okay. And then the last two topics are going to be constant acceleration, okay, 2D, all right, and here we have actually 4 equations, all right, but I would memorize these equations. Even though this is going to be an open book test, I would still memorize the equations, and the reason I would do that is because just the act of memorizing them and thinking them through, as you memorize them, you're going to see patterns in them, and it makes solving them so much easier, okay, rather than wasting time during the test and trying to rethink them. So if you take a look at the first 3 here, so there are 4 equations for 2D kinematics. If you take a look at the first 3 equations here, these ones, they only involve y. They don't involve x at all, okay? And so the first one, take a look at it. It's y is equal to 1/2 ayt squared plus v naught yt plus y naught, okay? And if you take a look at that equation and you go back to the 1D kinematics problems, like this, right here, you take a look at that one, you'll realize that they're really the same equation, okay? Now, this one has x because when we had 1D, we just had one axis and we called it x. But in 2D, we have two axes, and we call the vertical axis y. And so you're just renaming x to y, And so you get the same equation, but wherever you had x in the first one, you have it replaced with y in the second one. Also, the velocity has two components to it, okay, an x component and a y component, and it's only the y component, or the y component of the initial velocity, I should say, right there, that's involved in this. Okay, so this equation is just like the first equation in 1D. This equation, same thing. All right, there it was v is equal to at plus v naught. Here it's the y component of the final velocity is equal to the y component of the acceleration times t plus v naught y. So if you put the two together side by side, you can see the similarity. And then just like in the other one, that third equation was the other two with time eliminated. You get the same thing here. Okay, so that's just why. So the first three equations are like the three equations for 1D kinematics, but repeated with x with y replacing x. Okay, and then we have that equation right there, which is the only equation in x. Okay, and so this pattern is those features there are actually important when you go to solve a problem. So if you have like one of these projectile motions, what you're gonna get is you're gonna get the y information, and the y information is going to decouple from the x information. Usually, I don't give you enough x information to be able to make use of that equation right away. That third equation, sorry, that fourth equation, the one that's highlighted there. You can't use that one right away. Usually, you're going to use one of the other two to start to unravel the problem. Something like, how long is the thing in flight? Okay, typically that's this equation right here, the first one, where you have to solve the quadratic. All right, and then once you get that information out of the y equation, then you can use it in the x equation to figure out how far something travels horizontally. Okay, so I don't want to do one of these problems because that was actually our last live stream, and it's also this week's assignment. So if you have problems with that, ask me during one of the Google Hangouts, and I'll be happy to help you pass that. But I don't want to do this because we just did this already. And then the last topic is uniform circular motion, and maybe we can do a quick little question with this, but these are also pretty easy. And I didn't make it obvious that these three equations are actually a repeat of the harmonic oscillator problem, but they are. Okay, it doesn't seem obvious at first, but there's actually like that. These are actually similar to the harmonic oscillator problems. So up here in the harmonic oscillator, you see how you have like omega is equal to 2 pi over capital T down here, and then you've got the V max, right, is equal to omega times A. If you take out that omega and you put in 2 pi over capital T, you get 2 pi A over capital T. We'll take a look at this equation here for the velocity. 2 pi, not A, but R, divided by capital T, okay? And the other one, which was A max is equal to omega squared A, that's actually like this one, okay? And so even these equations are quite similar to the other ones, all right, for the harmonic oscillator. And the reason is that uniform circular motion, if you squish out the x component of uniform circular motion, you get harmonic oscillation. Because if you've got something which is going in a circle, that's what uniform circular motion means, something which is turning on a circle like that at the same speed. If you squish that out, that motion out, you're going back and forth like that. You squish it out, eventually it just squishes to something that goes back and forth like that. Okay, so let's do a problem with uniform circular motion. Maybe I'll go back and I'll do one conversion problem because we do have some time here. But uniform circular motion, any motion which is on a circle and where the velocity is constant, okay? And so it can't be, it's on the circle and it's always turning, but it can't be speeding up or slowing down as it goes around the circle, okay? So, the usual problems here are driving around a corner, or what's another example? Centrifuges. I think that's the example that I gave in the assignment, where you have things that spin, okay, and they produce a lot of acceleration. That's the way of separating blood in test tubes, okay. As the centrifuge spins, it produces a lot of centrifugal acceleration. That's kind of like artificial gravity, and it'll cause something to separate, like blood or whatever. And maybe we'll do just something going around a corner. So like a car travels at 15 kilometers per hour around a corner with radius what, what's a typical radius? Let's say 10 meters, like that. Okay. And I ask two questions. The first question is, well, let's just ask one. Okay, what's the centripetal acceleration? Okay, so what's the acceleration that you feel as you go around that corner? All right. I was going to ask for the period, but the reason I'm not going to ask for the period is because you're not going to make a complete. Um, you're not going to go around the corner. It's the whole corner isn't one complete circle. Okay, so let's just do the centripetal acceleration. All right, you feel that when you go around a corner, you know how you feel like you're kind of being thrown out. Actually, what you're doing is you're leaning in towards the middle to create centripetal acceleration, and that's exactly what's going on there. That centripetal acceleration is what's causing you to turn around the corner. Okay, so let's do that problem. The velocity v is 15 kilometers per hour, like that. And we got to do this in MKS. So take 15 and divide it by 3.6. And that gives me this. And let me round that off to 4.17 meters per second. Okay, so what I did there was I just took 15 kilometers per hour and converted it to meters per second. And just like above, it's like multiplying by 1,000 and dividing by 3,600, or conversely, just dividing by 3.6. And I got a velocity of 4.17. That car doesn't speed up or slow down in the turn. Okay, so it's going constantly at 4.17 meters per second as it goes around the corner there. Okay, and the radius, well, I gave it to you directly, is 10 meters, like that. Okay, and I want the acceleration. And here's another pattern you'll notice. The first two have time in it. They actually have the period, not exactly time. Period is the time for one full cycle. Okay, and the third one doesn't. Okay, and so whenever you have a problem that doesn't have any time information in it, any period in there, you use the third equation. Okay, and so here you want to use that equation right there. Okay. And we don't need to rearrange anything. We can just plug in 4.17 squared divided by 10. And let me see what that works out to. Oh. 10. There we go. Turns out to be this number right here. 4 meters per second squared, like that. Okay. So let me do that again because I've been having some calculator issues. Yeah, that is correct. Okay. All right. Meters per second squared. Is that a reasonable number? Well, that question, is it a reasonable number? You have to think of an acceleration to compare it to. Just like above, compare it to the acceleration due to gravity. Acceleration due to gravity is about 10 meters per second squared. This one is 1.74 meters per second squared. Yeah, it's a fraction. If you actually had like 10 meters per second squared as a centripetal acceleration, you would literally have to lean into the turn with the same weight that you're being pulled down by gravity. That's quite a turn. Okay, that's more like a carnival ride. Okay, which incidentally is another set of examples you could think of are like carnival rides. Okay, let me see if there's any questions there. Why is the radius 4.17? No, it's not the radius. It's not that the radius is 4.17. It's the velocity is 4.17 right here. So the velocity is 15 kilometers per hour. Okay, and 50 kilometers per hour turns out to be 4.17. So A is equal to V squared over R. V is 14.17 and R is 10. Okay, so it is correct. All right. Let me see if there's any other questions. Yeah, okay, so Zach did answer. V is 4.17. Exactly. It's V is equal is 4.17 meters per second. All right. We have a little bit of time. There's not too much more I want to do here, but let's just do one vector conversion problem here. Okay. And the harder ones are going from Cartesian to polar. And so let's say convert x is equal to, I don't know, -3. Let's make it more complicated. Y is equal to negative 4.7, like that, to a polar. Okay, so let's do that. Okay. All right. So how do you do that? Well, first, I mean, I give you x and y, and you want to go to r and theta. So obviously, you want to use the second set of equations. Okay, you want to use these two. Okay, and let's get the magnitude first. So the magnitude means like how long is this vector, or how big is this vector, irrespective of the direction. Okay, so like, like in a lot of my problems when I have the projectile, I'm firing something at 25 meters per second at 30 degrees above the horizon. It's at 25 meters per second, which is the magnitude, because it's like it's going 25 meters per second. I don't care about the direction. Just put the direction aside. How fast is it going, irrespective of the direction? 25 meters per second. So this vector, it's like, how long is this vector, irrespective of the direction? That's your r, also known as the magnitude. Okay. And so here that's going to equal the square root of, all right, and it's -3.5 all squared plus -4.7 all squared, like that. Okay, and square the negatives along with it. So I wrote the negatives in there so you could see what I did, but when you square a negative number, the negatives go away, so that's going to be exactly the same as that. Okay, so where did the negatives go? Well, when I square them, they just drop out. So let's see what that works out to be. It's going to be the square root of 3.5 squared plus 4.7 squared. Okay, and that's equal to this, and then round it off like that. Okay, so there's your r component. Okay, I'll put the negatives in there just to, I don't know, if you read your notes later, you want to know where did the negatives go, but they're there. But again, you're just squaring everything, including the negative, and a negative times a negative is a positive. All right, and then the next one is the angle, and this is the one that's complicated, because you could actually see here that I have in brackets add 0 degrees or add 180 degrees or add 360 degrees. If you're in quadrant 1, you don't add anything. If you're in quadrants 2 and 3, you add 180, and if you're in quadrant 4, you add 360. And the reason for this is just because the inverse tangent function has different branches, and your calculator doesn't know that. Okay, your calculator only gives the value on the one branch, and so you have to compensate for that. Okay, and so let's do this. It's going to be the inverse tangent of y over x, and you have to ask yourself, what quadrant is this in? Okay, what quadrant is that in? If you have to sketch it, you can. Just realize, if your x is negative and your y is negative, you're actually in quadrant 3, and so in quadrant 3 you have to add the 180 there. You can just say to the side here, add 180, because we are in quad 3. Okay, and so that's going to equal the inverse tangent of, and let's put these numbers in here. So it's -4.7 divided by -3.5, negative in the denominator, so the negatives actually cancel. Okay, as a result, the inverse tangent piece doesn't know whether this is in the first quadrant where they're both positive, or it's in the the third quadrant where they're both negative. So that's what's going on here. Because the negatives, these two negatives cancel out there, okay, the inverse tangent can't distinguish between first and third quadrant. You have to distinguish. First quadrant, add nothing. Third quadrant, add a 180. Okay, and so that turns out to be, let me work that out, inverse tangent of 4.7 divided by 3.5, like that. So I'm just going to write this in 2 steps, like that, plus 180 degrees, like that. So, okay. If you hadn't added the 180, you would have gotten 53.3, which is in the first quadrant. But because we have to add the 180, you're going to get plus 233 degrees, which is in quad 3. Okay, so that's how you do those ones. All right, let me see if there's any questions in the chat here. Um, there you go. We've actually done an example of each type of question, with the exception of the 2D kinematics. Okay, so I'm gonna call the say this is the end of the lecture, unless you guys have some other questions, and try to work on the assignment with that 2D constant acceleration problem. Try to do it today or tomorrow so that you can ask me questions before the test on Thursday. Let me just end by saying, what the test is going to be like, and like how you get on the test. Just what'll happen is that I'll email you. I'll put these instructions in an email anyhow, probably tomorrow. But I'll email you and I'll say, look, a few minutes before the test, I'll say, hey, the test is ready. And then you log into your Canvas site and you'll see the test there. Okay. And you can start it. When you start the test, you're going to have 2 hours from when you start it. If I'm not mistaken, it doesn't matter that if you start a little late or a little early or anything like that. You'll have 2 hours, and so you always get the full 2 hours, no matter, even if you start a little later. And you'll only get, obviously, the chance to do it once. All right, and it won't tell you the right and wrong answers like it does on the assignment. Okay, and the reason for that is because I want to wait till everyone's done, and then we can go over the test together. Okay, I don't want because it's possible for people to share answers during the test, because someone can do it earlier than someone else. And so to prevent that, you won't actually see the answers, the correct answers of what you did wrong. You'll get your grade, but you won't see the correct answers right away. Okay, we'll go over the test afterwards. Okay, so if there are no other questions, then this is the end of the stream. Okay, so I'll just wait a few more minutes to see if anyone has any questions. And yep, thanks, Zach. All right, bye-bye, everyone. Gonna end the stream in a few seconds here.